Okay, here we go. Third to last unit, right? Second to last, or is that third to last? Third to last? Or second to last? Anyway, doesn't need to be on the video, so I should shut up. Okay, so the acid-base equilibrium, as I have already warned you, is one of typically the toughest units for AP Chem students across the board. It's basically two parts. There's the acid, base, and aqueous equilibria, and then the second half, which we'll get to next week, is buffers, like when we titrate acids and bases. And if we're titrating straight up strong acids with straight up strong bases, it's very easy, it's whatever. But when we start throwing in weak acids or weak bases with their strong counterpart, we get buffers, and the system does something different. And so there's quite a bit of calculations with that. And that's the part of the unit that gives them more trouble than this part. Okay, so we're going to start with the easy part. Start with some definitions. Acids taste sour, right? We're going to get to pH in a minute, but from our memory banks, if it's an acid, what does it have a pH of? Less than 7, thank you. And if it's a base, we also call those alkali, they taste bitter and feel slippery, okay? And then their pH, of course, is above 7, right? And if you're 7 exactly, neutral. So see, y'all learned something before. Here are the 3 basic definitions in terms of their inclusivity, if that's a word. Lewis is your broadest definition, okay? It is no longer tested. Oops, that is not writing real. It is the broadest definition, meaning more things would be considered an acid or a base under the Lewis acid-base system. In that case, your acid is the electron pair acceptor, and your base is an electron pair donor. Bronsted-Lowry is your middle definition. It's actually the most common one that we use. It's the one that has the conjugate acid and bases. Do you remember that from pre-AP? And it says that the acid is the proton donor and the base is the proton acceptor, meaning the proton is an H+. And then the Arrhenius, same thing for acid definition, proton donor, but the difference for the base is it says it's an OH donor. And so some things that we consider base, like a weak base, would not be considered a base under the Arrhenius. So that's the strictest definition, is the Arrhenius. Okay? Lewis acid base is no longer tested on the AP exam. So we talk a little bit about it and then we're done. Okay? So that's going to take us to hydronium. We got to remember what that is. Remember that's the H3O plus formed when you have a reaction with water. The H plus and the H0 plus are used interchangeably in most situations. Most of the time we say H plus, but when we say H plus, we are in fact saying hydronium, and that is water accepted an extra hydrogen, and it's H3O plus. Okay, but for brevity's sakes and all that, most of us say H plus. Okay, like when we say pH, we don't say pH3O plus, we say pH, which is the hydrogen concentration. Just a refresher, remember conjugate acid and a conjugate base, they go together with the opposite. So acid goes with conjugate base goes with conjugate acid, just so you remember that. So basically the conjugate base is what happens after a proton. The conjugate base is of the acid, what happens when it gave it up. Okay, so if you look at HA, the conjugate base is the A minus. So the conjugate base will always have one less hydrogen than the original acid. And then the conjugate acid is the base plus proton. So it will always have one more proton than the original base. Okay, so the difference between them is a hydrogen, basically. Okay. So let's do this real quick. Let's label it. Okay, which one is the acid? Which one is the base? You tell me. Which one is the acid? HBr. And so that means this is going to be its conjugate base, right? I find what happens when I lose my hydrogen. And then this, of course, is the base. And then this would be the conjugate acid. All right. What is the conjugate base of H2S?
S2 minus? Maybe S2 minus or S minus?
Okay. It's one hydrogen difference between the conjugate. Only a one hydrogen difference. And then what would the conjugate acid of NO3 minus be? I just realized I did not subscript those.
They're subscripted on ours.
Yeah, when I copied it over, I didn't go, yeah. They are subscribed on your notes?
Yes.
Okay, good. All right, so we feel pretty comfortable with that. Okay, hopefully. Okay, so here is a question. You have H2CO3 plus water going to HCO3 minus plus H3O plus. Which of the following represents the base conjugate acid-base pair in the equation shown below? Which is your right answer? Which one can we throw out immediately because they make no sense?
A and C.
He says throw out A and C. Okay. Couldn't I also throw out B? The answer was, oh, sorry, the answer was D. I thought it came up, it didn't. So this are what our acid-base dissociation constant looks like. Still products over reactants, okay? And that's assuming that we have HA, which stands for, that's our standard representation of a weak acid, plus H2O yields H3O plus A minus. We can also show it just as the dissociation of this, and the water is assumed to be there. Okay, so why is water not included in this expression? Why did we not include water? It's a pure liquid. Yeah, we didn't write it, but it is a pure liquid, so that's why water is never included in the expression. Okay? All right, so generally it's the hydrogen, the conjugate, over the acid. Okay? Okay? Oops, too far. Sorry about that. Strong acids, of course, we need to refresh our memory on that. Strong acids have to do with their ability to dissociate, okay? Doesn't necessarily have to do with their pH. Some of our weak acids still have a pretty low pH, and so some people get tripped up on that. And they go, it's a weak acid, so it should have a pH of much higher. But some weak acids still have a high pH. But it's 100% dissociation, almost 100%. The equilibrium lies very far to the right, so it would have a very, very large Ka value. In fact, we don't give Ka values to strong acids. They're too big. They mean nothing because it's pretty much goes to completion of dissociation. Okay? If you have a strong acid, this is going to be important. Underline it. If you have a strong acid, it will yield a weak conjugate base. Strong gives weak, and what do you think weak gives? Strong, exactly. So a weak acid means mostly undissociated. Equilibrium lies far to the left, and it has a very strong conjugate base because it came from a weak acid. Stronger than water, but it's not a strong base. Okay. Okay. Those strong acids that I listed a while ago, a couple of slides ago, or it's not, I have not got there yet. I'm ahead of myself. Blank slide. Oh, I put that up there because it's really important for you to remember. The weaker the acid, the stronger its conjugate is, and vice versa. So there's a visual, very strong, going to have a very weak conjugate base. And then there's a difference in dissociation before and after, so you could recognize whether it was a weak or a strong. Okay, drawing time. I'm going to pause the video while you draw the 5. This is where we read our directions, because some of you on a quiz a while back or a test didn't see that it said 5 and you drew less. Sketch 5 molecules of HF and 5 molecules of HCl, what they would look like in a beaker of water. Go. I'm going to pause it while y'all draw. All right, so what should that look like? For HF is a weak acid. You even told you it was weak acid. And HCl is a strong acid. So for your HCl, it should be completely dissociated, nothing connected. For your HF, generally when you've got 5, you're going to draw one. You're going to draw one dissociated, the other 4 left together. Okay, so you would keep them connected. Okay, any questions on that?
So they didn't want us to show how the water molecules were surrounding?
No.
Okay, because that's what I did.
No, you didn't have to. I mean, they wouldn't say that's wrong, but generally in this case, they're just saying, hey, they know that the water's going to be surrounding it. Yeah. Okay. Unless they say represent the water molecules are assumed to be there. But it wouldn't be wrong if you drew it and you didn't need to.
Because it was a little bit cluttered.
Yeah. Okay. Now we are going to arrange the following species according to their strength as bases. Okay? According to their strength as bases. So, trying to see if I want y'all to do this. I think I want y'all to try that, and then we'll come back together. So y'all try it and see what you think. Let me see where your thought process is. Okay, so what you needed to do here was it asked for according to their strength as basis. So they want you to say strongest base to the weakest base. So what we need to do here is see what acid did they come from. Okay, because a weak acid will give a strong base, a strong acid will give a weak base. So I know immediately that HCl is the only strong acid that I have listed there, so it's going to be last in terms of strength as a base for Cl-. Okay, water, of course, is going to be somewhere there in the middle. And then I look at my other 3. I've listed my Ka values, so that was a pretty big hint right there. To be quite honest, without the Ka values, you wouldn't be able to distinguish between the ones that come from a weak acid. You got to have a Ka value. The smaller the Ka value, the weaker the acid. Okay, so in this case, HCN is the weakest acid, which is going to give us the strongest conjugate base. Okay, and so then I just listed them in order based on that. Okay.
Wait.
Yes, your question?
Say about the Ka values.
A Ka value, a very, 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 the smaller the Ka value, the weaker the acid. The weaker the acid, the stronger the conjugate base. Like whatever it gives you is opposite.
So is it considered a weak acid if its K value is less than 1? Is that the cutoff?
So, no. The negative, HF is a fairly weak acid. Acetic acid has got a -5. I'm not really sure where that, I'd have to go look at some Ka values of all the acids and say, but generally if it's a strong acid, it has a very large Ka value. They don't even list it. Like it's hard to find a published value for it.
Okay.
Yeah. Adam?
So how do you know the ranking of the 5 if you only have 3 values?
Well, so I know that HCl is a strong acid, right? Okay. So HCl is a strong acid, so it's going to make a weak conjugate base. So it's going to be the weakest base.
So we have to just go out on a limb and hope it's the weakest base. You know from chemistry knowledge.
No, you wouldn't be going out on a limb if you for 100% you're going to have to memorize the strong acids.
Well, yeah.
Okay. And so if you know it's a strong acid, generally they're not going to give you in a list like this, they're not going to give you 2 strong acids. Okay? They're generally not going to do that. They're going to give you Ka values in there. Well, water is, we're going to find out in a minute, is something that's amphoteric. It can be an acid or a base. But it said a while ago, when we have a weak acid, it will make a stronger base than water. Like 2 slides ago, it said when it makes a conjugate, it will be a stronger base than water. Okay. Okay. Come on. Here are your strong acids. I cannot stress this strong enough to you to memorize them. There's not a lot that AP wants you to truly memorize. They want you to understand it, but you've got to memorize the strong acids. Okay? There's just no way around it. Okay? So you have the halogenic acids, which are HCl, HI, HBr. HF is not one of those. We'll talk about that in a minute. And then you've got the sulfuric acid, the nitric acid, and the chloric acid. Okay? Acids will donate 1 proton at a time. So a while ago when I said, what's the conjugate of H2S? And someone said, I think it's S2-, that makes sense, right? I get rid of the hydrogen. But the thing is acids only donate 1 hydrogen at a time. You'll see that in some of our calculations, okay? Because we're going to have to do First dissociation, second dissociation, third dissociation. Okay. All right. Sulfuric acid is a diprotic acid, which means that it has two acidic protons. The first, H2SO4, is strong. The second, HSO4 minus, is weak. Okay, so the first dissociation is a strong dissociation. The second one is a weak. So we have monoprotic, diprotic, and polyprotic acids. That's pretty self-explanatory. Mono means it donates one hydrogen, for example, HCl. Diprotic has 2 to give, H2SO4, and polyprotic has 3, which is H3PO4, meaning it can dissociate 3 different times. Oxyacids are, matter of fact, most acids are oxyacids, and that is they have an acidic proton is attached to an oxygen. Okay, and so this would be HNO2 right here. And these are weak, they tend to be weak oxyacids, and there's a couple of examples. Okay? Within a series, in other words, like perchloric, chloric, chlorous, and hypochlorous acid, within a series, this acid strength increases with the number of oxygen. So HClO4 is a strong acid, HClO or HClO2 is not. Same thing with sulfuric versus sulfurous, nitric versus nitrous. The one with the higher oxygen is strong. Stronger, not always a strong acid, but stronger than the ones with less. And that is because the electronegative oxygen draws electrons away from that OH bond. So the more oxygens you have to draw that away, okay, and it makes that bond easier to break, which makes it a strong acid. So it's kind of a misnomer, like HF is not included in the halogenic acids, right? So we think, wow, but that's a really strong bond. Okay, it's really electronegative. Well, it's because it's a really strong bond that you can't easily break it apart so that it will dissociate in water. And then there's just talking about the electron density. So if you look at that, it kind of shows you how that's able to pull that away so that HClO4 will completely dissociate. So it breaks apart at that OH bond. Acid strength increases with increasing electronegativity of oxyacids. So if I look at this series, HOCl is going to be a stronger acid than HOBr because chlorine is more electronegative. Okay. And then we have a class of compounds called organic acid. The one that you are the most familiar with, of course, is acetic acid. When we see acetic acid, we need to recognize it like this and like this. We need to recognize both ways. Okay, depends on who wrote the question if they're going to write it the way the organic chemists write it or the way the inorganic chemists write it. But now you can kind of see why they write it this way, the organic chemists, because that's exactly what it looks like when you draw it out structurally. CH3COOH. Okay? Whereas the HC2H3O2 is just the inorganic chemist way. And they can't get together and decide how to do it. Primarily because initially this would be hard right here for us to recognize as an acid, because we're used to seeing the H come first. So you need to also recognize CH3COO. Hydrohalic acids are, of course, attached to a halogen. And then this is talking about HF is the only weak. We just talked about this. And though it's a very polar bond, the bond is strong because of, you guessed it, what am I going to say? Coulombic attraction. It's due to the Coulombic attraction due to size, distance. Okay, the HF is a small atom, so the A and the F is very small, so they can get really close together and have a really strong Coulombic attraction, which is why it doesn't like to ionize in water. Okay. Weak acid strength is compared by the Ka values. The smaller the Ka, I already said this, the weaker the acid. Strong acids do not usually have a Ka because the HA is so small and cannot be measured accurately. Meaning if you go back to the expression of Ka is equal to H plus, A minus, and then you have the HA. Well, because it's such a complete dissociation, this number on the bottom is so small that they can't really measure it. So then your Ka value can't be measured accurately because you don't have a number on the bottom because it's a complete dissociation. Amphoteric is something that can act as an acid or a base, meaning it has the ability to lose a proton or gain a proton. Water is the most classic example of that. Water can gain a proton and go from H2O to H3O plus, right? Or water can lose a proton and go from H2O to OH minus. So water is amphoteric, and it will depend on, excuse me, what water is reacting with. If water is reacting with a weak acid, it'll act as a base. If it's reacting with a weak base, it'll act as an acid. That's the way it does. So if you're trying to figure out, hey, is this water being an acid or a base, then you look at what it's reacting with and decide what that is. And that brings us to the autoionization of water. Water can autoionize itself. Isn't it special? Okay. And that's exactly where the one acid that, this one right here, let's draw a picture. This one right here, base, right? It accepted and became a conjugate acid. This water gave it away and became a conjugate base. Okay? So it has that ability to do that. The cool part of that is in pure water, your concentration of H and your concentration of OH minus is exactly the same. That's what makes something neutral, is their concentration of hydrogen and hydroxide ions are exactly the same. Okay? Looks like this. Okay? Kw is the ion product constant for water. At 25 degrees Celsius, it is 1 times 10 to the negative 14, and that is because in pure water, the hydrogen is equal to the hydroxide, which is 1 times 10 to the negative 7 molar. And that's in pure water at 25 degrees Celsius. That is temperature dependent. If I change the temperature, I change my Kw value, which would then in turn change the H plus and OH if it were neutral. Okay. Okay. We're almost there for today, and then we're stopping. No matter what, an aqueous solution at 25 degrees Celsius always has 1 times 10 to the negative 14 as the product constant. If it's neutral, they're equal. If it's acidic, then you have more hydrogen concentration than hydroxide. If it's basic, you have more hydroxide than hydrogen. Simple as that. pH scale. I know that the P is supposed to be little on my slides. This particular design only would let me do in caps, which was kind of a pain. And I didn't realize it until I got to this point, and I didn't want to change it, so I'll be honest. Just left it. So those are supposed to be little p's, big h's. Okay? So it's negative log of the hydrogen concentration, POH, negative log of the hydroxide concentration. Together, pH plus POH equals 14. And then, of course, if I have the pH and need to go to concentration, I can take the antilog. Okay, 10 raised to the negative pH will give me the hydrogen concentration. Those formulas are going to be very important to us, so keep them in mind. We don't need this right now, but we will later. A pKa is a negative log of your Ka value. Okay, I just wanted to put that in there because we're going to see that later. Okay. There you have, we already talked about general scale, acid and base, we know what those are. Just blood is actually slightly basic, so you're all slightly basic. Yeah. Significant figures in pH. We talked about this in Chem 1, but I would imagine my seniors do not remember that from from sophomore year. But the pH is, when you do significant figures, you're looking at the decimal places in your pH are going to be the same as the significant figures in your concentration. Right? So if I have 0.25 molar, that's 2 sig figs, I need a pH with 2 decimal places. Bam. And I am going to show you probably tomorrow. I have just a short little quick YouTube video of how you can estimate pHs without a calculator, because you will be expected to do that on multiple choice. Okay? If you're doing a pH of a log of 1 times 10 to the negative 7, it's easy. Or if I have a pH, but if I start doing like 2.5 times 10 to the negative 3, that's not as easy to do. So I'm going to give you a little quick video on how to do that. It's not hard, actually. Yeah, it's not hard. I mean, I could tell you the way I do it, but it might not make sense because it makes sense in my head. The video makes better sense of what I would say. Some of those things you just know, right? Okay? So if I had a pH of 4.42, it has 2 significant figures. That means I would put my concentration in 2 significant figures because of the 2 decimal places. Because basically that first number, 4, is the power of the log 10. So it's telling you, you know, where you're at. Okay? Of course they are, you already know this because you do math. Is someone here? pH and pOH are logarithmic function, of course, so they changes by 1 for every power of 10. So a substance with a pH of 3 has 10 times the hydrogen as a substance of a pH of 4. Which kind of, we don't think about that when we say, oh, it's a pH of 2 or a pH of 3. We think, oh, that's still really acidic. But that's actually quite a bit difference in the hydrogen concentration. This is the last thing we're going to do today, is calculating pH of a strong acid solution, because it's way easier than a weak acid solution. You take the negative log of the concentration. Simple as that, right? Okay. Exception to that would be when we're doing the pH of H2SO4, sulfuric acid, because it has 2 hydrogens, right? And it dissociates in 2 steps. So if it's more dilute than 1 molar, we're going to have to do the first one as a strong and the second one as a weak, which we're not going to do till tomorrow. Okay, it says you won't be, we're doing it anyway. It says it won't be involved on the AP exam probably because you have to do a quadratic equation. I wouldn't take that to the bank. They've never said quadratic equations don't show up on the AP exam. It's just historically they never have. So I would be remiss to not show you how to do it. Okay, so here's some examples. You can do these. You have a calculator. I'm pausing. Go. Okay, so this is HCl is a strong acid, so the concentration is simply, in this case, because it's monoprotic, it's simply just 1.0 molar. That's what they gave us there. And then in order to get the pH of that, we're going to take the negative log of 1.0, which gives us, guess what? 0. Yeah, okay, 0. Okay? Now that means the next one says calculate the pH of 1 times 10 to the negative 10 molar. So our hydrogen concentration is 1 times 10 to the negative 10. But it would make absolutely no sense for me to do a negative log of that and tell me the pH is 10, would it?
I did it anyway.
Okay, but how many of you did that anyway? Said the pH is 10. No, pH is 7. Because remember, in an aqueous solution, aqueous is water, hydrogen concentration is 1 times 10 to the negative 7. So right now we have more hydrogen coming from water than we would from the HCl. So it's a bit of a trick question.
What?
Okay, let's go back. Let's go back.
Doesn't make any sense.
Okay, what if it's an aqueous solution? It's dissolved in water. Okay, right? Okay. The only thing they're saying is that we put this would be like putting a drop of acid in there. Okay, right? Be very little. 1 times 10 to the negative 10, hardly anything. But water itself has a concentration of hydrogen of 1 times 10 to the negative 7. Okay? Which would be 7 as neutral. Does that make sense now?
So we're not taking the
Yeah, but that's stupid.
Because this is, pay attention to what you're looking at, yeah.
You're saying that it's a
Does the
basic
quantity
solution.
of that even matter?
Huh?
It could be any quantity.
What do you mean it could be any
Like,
quantity?
how much acid do you have to put in before you take the concentration of the acid?
Well, so because neutral is 1 times 10 to the negative 7, it'd be different if they were giving me also a hydroxide concentration here. Okay? It's like if I was doing this with a hydroxide and I had a higher hydroxide concentration, then yes, I could have that low of a hydrogen concentration. And then it would be a pH of 10. But we don't have any hydroxide here. We're just saying I had some water, I put in a concentration of 1 times 10 to the negative 10 molar HCl. What is my pH? What I'm saying is the hydrogen from the water is contributing more to the pH than the tiny bit that 1 times 10 to the negative 10 molar would be.
Just water.
It is, well, I don't want to say basically just water. It is water, yeah. Yes.
So if it said like, instead of 1 times 10 to the negative 10, if it said like 1 times 10 to the negative 6, would it be 6?
Yes.
But shouldn't we always work on the additive basis? Like we should just add the H plus that's coming from that.
So if they try and trick us and give us a like a 1 times 10 to the negative 7 concentration of HCl, should we add that to the hydrogen that's coming from the water into the 2 times 10 to the negative 7?
No. I mean, most of the time we're not going to be taking the water over the other stuff. Most of the time, but this is there so you can see that at some point your pH is going to be from the water, not from that. That's a minuscule amount. 1 times 10 to the negative 10, minuscule amount. Okay. Because the water, that is the concentration of hydrogen in water, okay, which is greater than this right here, right? Because these are all in aqueous solutions, and so then your pH would be 7. Yes, Adam.
So if it's any number less than what water is, we're just staying together.
Mm-hmm.
Or if it's bigger than.
Yeah, or if there's some hydroxide involved, like if they've said that they put some hydroxide, because even when it's a basic solution, guess what? There's still some hydrogen in there because it's in water. But now the hydroxide is so much higher than that, okay? And I think that that might be where we're stopping.
Wait, so which one has to be raised to the negative 6 from pH?
The hydrogen? Yeah. Okay, that's where we're stopping, yeah.
Slash the